Hello everyone and welcome to this first tutorial for the business analytics course, which is going to be on distributions. So today, Dr. Malolan is joining with us and he's going to take us through the task of identifying distributions and fitting distributions. Hello Malolan.
Hey Swami.
So today we have three interesting data sets. So our task is to guess the distribution first and check whether the guess is right. Would you like to add further?
Yeah, so usually in business problems, the first order of business is to find out a distribution. And this tutorial video is going to be about that. And like Swami said, we are going to look at three different data and try to find the distribution for it. And usually the approach that we take is that we first look at, let's say, descriptive visualizations, then use descriptive statistics to further identify distributions, and then finally we go in for actual tests to confirm our judgment. So that is what we usually do, and we will demonstrate that using Python today.
Yes, as discussed in the course outline, the emphasis of this course will be not on coding. In fact, we'll give you the codes and the dataset. You can run and practice these fitting distributions yourself. So therefore, the emphasis will be more on the interpretation part and not on the coding part. So with that, so let's get started. So first of all, let me show you the data set first. So in the lecture video, you would have seen Professor Rahul, he wouldn't have mentioned the business case first. So he would have shown you the data first. And after guessing the distribution and fitting the distribution, later he would expose you to the business case. So we'll follow the same approach. Right now, I'm not going to give you the business context. First, we'll look at the data set. We'll guess the distribution. We'll do some statistical tests and then look at the business case. So first, I'm showing you the Excel file. Then we'll load this Excel file to Python and do the required steps for finding the distribution. So this is the data set. It's a beautiful data set because it has only one column and the column name is observations or OBS. And if you look at the count, so we have around 101, out of which one is the header. So there are 100 data points available with us. So without any further delay, let's load this data set into Python and then start with the descriptive statistics. So you might be already aware of the Python software. You could do it in multiple IDEs. So we are using Google Collaboratory. You could also do the same with Jupyter Notebooks, Spider or PyCharm, whichever is of interest to you. So let me upload the data set, which is data1, which is also an Excel file. So we have uploaded the data set, and then I'm going to import certain libraries, which you're already aware of, Python, Pandas and NumPy. And then I'm reading the Excel file. So now let's look at this data frame. If you look at the data frame, so there is one column, 100 rows, and we cannot say much from this. So therefore, let's get into some visualization like histogram.
Yeah, just to add to those who are comparatively newer to Python, whenever you upload a data set, if you can just scroll up a bit, Swami.
Sure.
Yeah. So if you see, the header is OBS and the values 5, 4, 4, 5, 5, those are the observations. And the column next to that is actually the index. So index 0 refers to the first observation, which is 5. Index 1 refers to the second observation, which is 4. So 0, 1, 2, 3, 4 is the index. And then you have the actual data that you are going to use. Just for the clarity of those who are new to Python. Yeah.
All right. From the histogram, so I've just plotted a histogram using matplotlib. So these are things which you're already aware of. So first I've plotted the histogram. So Malo, so does this histogram tell us a story?
Actually, histograms are very, very interesting graphs, and all of you, whenever you get any data and you want to find the distribution, the first order of business is to plot a histogram. And the beautiful question there, Swami, whenever you look at a histogram, you can look at it and tell what family of distributions a data set may belong to. So looking at this, one thing that we can say that it could be a non-Gaussian distribution since there are two peaks instead of just one. That is the first observation. But you cannot say whether it is a symmetric or non-symmetric distribution. So for that, we need to do further graphs.
Very true. So very well said. So with that, let us do some descriptive statistics. So df.describe is going to give us the basic statistics like count, mean, standard deviation, and so on. So we have a mean of 4.94 and standard deviation of 2.38. So the minimum value is 1 and the maximum value is 11. And then we have median at 5. So we may not conclude certain things from these basic descriptive statistics. So let us do some more descriptive statistics like kurtosis and skewness. So the next line of code is going to give us kurtosis, skewness, variance, and mean. Malo, if you observe this, the variance and mean are kind of close to each other. Not exactly close, but they're somehow pretty close to each other.
Exactly. So from the histogram, we actually said it's a non-Gaussian distribution, but we did not know which it could be. So at this point, maybe our viewers can actually pause and think about what distribution would have a mean and a variance almost close to each other. And the answer to that.
So that's the best clue for guessing this particular distribution, mean and variance.
Yeah. So the answer to that would be a Poisson distribution. So we can say with some amount of certainty using the histogram and the descriptive statistics that you have actually plotted to conclude that this data that is given to us can be a Poisson.
Yes, exactly. And also we have some kurtosis, which is negative 0.38 and skewness of 0.51.
Exactly.
So this also tells us that we can eliminate certain symmetric distributions.
Exactly, such as
normal, uniform.
Normal gets eliminated when we say non-Gaussian, no?
Yes.
So in the histogram, we will usually eliminate normal, but we still have distributions such as uniform, which would have peaks, but it's also a symmetric distribution. So that can be eliminated using the kurtosis and skewness.
Yes, so very well said. With that, let's also look at the median, which may not give us a lot of insight.
But it is interesting. It is a symmetric distribution, right? So the median is 5, the mean is also 5, which means 50% is lying below and 50% of the points are lying above. So it's still a symmetric distribution, but Poisson is not a symmetric distribution. So for that,
we still do not have enough evidence to conclude that this is this is Poisson.
Poisson, exactly. Exactly.
All right. So the best way to do that is by means of statistical testing, which is chi-square goodness of fit, for which we need to have data in certain format. So let's build our data frame. Let's make it in a way that is understandable for the Python language. So I'm importing certain libraries like statsmodels.api and scipy.stats. And then, so before getting into the statistical testing, so can we have a look at certain interesting plots like QQ plot and PP plot, which was already covered in the lecture by Professor Rahul. Okay, so we have a PP plot. So what does this say?
This says, all right. So in Python, the first thing that we have to understand is, in Python, whenever we run a code for any of the plots, it's always comparing it with the standard normal, and it's going to give you a conclusion. We will not go into depths of what PP plot is, what QQ plot is, but just an overview. So in a PP plot, we are going to compare the standard normal without any code. We are going to compare the standard normal with the actual distribution, the sample that we have got, and we are going to compare the cumulative distributions of both. And if both come from the same population, then they will lie on a straight line, right? So this particular plot that has been plotted, it's showing you that they are not lying on a straight line. They are not lying on the red line. They are actually parallel to each other, which means the data is not coming from a normal. All right. So that is what can be concluded from this particular PP plot.
Also, the other interesting thing is that since this deals with CDF, which is the cumulative distribution function, so we have data similar to a step function, which also gives us that this distribution could be discrete in nature.
Exactly. Fantastic. Yeah.
So therefore, the next step is to fit this PP plot with the Poisson distribution. So right now, as you said, by default, it is comparing the given data with standard normal distribution. So now why don't we try it with Poisson and check how the PP plot is?
Exactly. So since we are choosing Poisson because our mean and our mean and our variance are almost close to each other, but it's still not conclusive because the median is also same as the mean. So we want to confirm with a more stronger descriptive or a visualization, say, and for that we are going to develop the PP plot. And for this PP plot, we are going to say the distribution is Poisson. So what can it happen? Poisson with a mean of 4.94. So that is the code that is going to run.
Exactly. So I use this syntax called stats.probability plot or stats.prop plot, which is nothing but the PP plot. And I'm having the observations here. So we have around 100 observations. So this means that you have a data frame and the column that we are using is observation. And the distribution is Poisson and the parameter here is 4.94. So this parameter we got from the descriptive statistics. If you can look at the mean observed is also 4.94. So therefore, I have this line which is stats.probability plot, df of observation and distribution is Poisson and the parameter is 4.94, which is nothing but the mean of the Poisson distribution or lambda. And if I plot this, oh, it looks beautiful.
Yes, now the points are almost around that same line. So which means that we can, with a certain degree of certainty, say that the cumulative distribution from which this observation or this data is coming is a Poisson which has a mean, which has a lambda of 4.94, right? So that is what the PP plot is actually helping us conclude.
All right. So with this, let's get into the data frame again. I think we might have even forgotten the data frame because we were into too much of visualization. So that's our data frame. So now let's group this data frame and see what are the frequencies and the respective bins.
So we are now going into a more statistical approach of establishing that it's a Poisson. So through a visualization, we have established that it is a Poisson. Now through a statistical technique, the chi-square technique, we are going to establish that it's a Poisson. And for that, we will follow these steps.
All right. So the first step is I'm creating an empty data frame called group DF. And in group DF, I'm creating a column called frequency. So in that frequency, I'm actually grouping by using observations and count. So if you look at this data frame, the 1 is nothing but the observation 1. So that is coming 3 times in the data set. If you look at 2, it is appearing 14 times in the data set. And likewise, we have 11 classes or 11 bins. And if you see, look at the tail end, 10 and 2, they are coming only 2 times in the data set. If you look at 9, it comes 5 times in the data set and so on.
Swami,
any comment on these things?
Yeah, so maybe as a, just as an explanation that the code is working fine, why don't you just open the Excel and put a filter and choose observation 1, for example. Yeah. You can just add a filter.
No.
Yeah. And now if you just filter the observation 1, it is appearing 3 times in the data frame. So that is what this has been done. So 1 is appearing 3 times. So if you put 2, it will appear 14 times. 3 is appearing 15 times. So why is this required? You will get to know in the immediate next pieces of code. So it is appearing 15 times.
14 times.
Yeah, 14 times. Yeah, 1 header. Yeah.
Right. Correct. So next, in addition to this frequency column, I'm creating another column called observed probability. So what does observed probability do? We can print and check it out. We're actually calculating the probability of 1 occurring in the data set. So for that, we divide this frequency by the length of data frame, which is 100. So if you want, we can check on those parameters. For example, if I just give length of the data frame, it's going to show 100, right? And frequency, you already know that was the previous step. So we are dividing the previous step by the length of data frame, which is 100. So now we have 2 beautiful columns. One is frequency and observed probability. And then we come to the most important step where we are calculating the theoretical probability. So right now we calculated the observed probability from the data set. So right now we're going to calculate the theoretical probability. For that, I'm importing certain packages which you already know. SciPy. From SciPy, I'm importing stats package, and then I'm also importing Poisson and chi-square. So if you look at this command, Poisson.tmf, so this is nothing but the command. So this function requires two important arguments. One is k, other one is the argument, which could be the mean. So let me complete this command. So I'm creating another column called Poisson TMF, where I'm using this function called Poisson.tmf, and we have something called k. And inside k, so let me run this and then show you what this k is. Let me add a column above. So let's see what this k means. Inside k, we have grouped underscore df dot index. So you have these 11 classes, right, which are available here, the observed, the index of this data frame, which means that we have the classes or the buckets as one of the parameters, which has been available inside grouped underscore df dot index. And next is nothing but the argument mu. Mu is nothing but the Poisson distribution parameter lambda. In our case, we have the mean from the data set. So let's also check what that means. So let's print this and check what this command is going to give us. It should ideally return 4.94.
4.94.
So therefore, I'm using this function called Poisson.tmf, where I've given two arguments. One is k, which has the group underscore df dot index, which indicates the number of classes, and then the next argument is mu, which is nothing but the mean of the observed values, right?
Mean of the sample.
Of the sample, yeah. So I think I'm just repeating those steps here, which are of not interest to us. So now let's print grouped underscore df. So right now we have three columns. One is frequency, observed probability, and observed PMF. Let's also create another column called Poisson frequency.
1 second, Swami. Maybe for those who are seeing this data frame now, the Poisson PMF is basically going to tell you, okay, let's say the observed probability is telling you from the sample, what is the probability of that observation happening. And so that is 0.03. Whereas the Poisson PMF is telling you from the population, from assuming that the population is a Poisson with a mean of 4.94, what is the probability of getting 1? So that is the difference between the two columns that are present in this particular data frame. So observed probability is in the sample, what was the probability of 1 happening? And Poisson PMF is basically telling you from the population from which this sample comes, if that is a Poisson with 4.94, then what is the probability of observing a 1 in that population? So that is the difference between the two.
Very well said. So let's create this new column called Poisson frequency and then print the data frame. So now we have 4 columns. So one is observed frequency, observed probability, Poisson probability, and Poisson frequency. So do they look close enough?
Yes, they do, right? You have the first one is close enough. The second one is not so much. Third is close, fourth is closed. So visually, it is somewhat matching, maybe 80% is matching. But is that match significant is what we have to answer.
Yes. And so also the Poisson frequency, I mean, since Poisson is a discrete distribution, and so we have this frequency in decimals.
Decimals.
The number of decimals are too much. So let's round it off to 2 so that it looks better. So ideally, it's the theoretical frequency. Therefore, you can have decimals. And now I'm creating 2 lists. One is observed frequency, other is expected frequency. And so this Observed frequency is nothing but the first column, which is this 3, 14, 15, and so on. And second one is nothing but the Poisson frequency, which is 3.53, 8.73, and so on. So let's also print that and see. So let's print. So that's our observed frequency. So similarly, if you print the expected frequency, right? So we have 11 in both. So now let's talk about the null hypothesis. So the null hypothesis, according to chi-square test, chi-square goodness of fit test, says that the data follows Poisson distribution. And the alternate hypothesis says that the given data does not follow Poisson distribution. So for this, we already have imported certain packages like chi-square, Poisson, and so on. So now we are going to do the test, stats.chi-square between the observed frequency and the expected frequency. So let's see how the test is performing. So we have a statistic, which is nothing but the chi-square statistic that says 7.91. And we have a p-value of 0.63. So Malo, so how do you go about this? Can we talk about the confidence level that we are looking at?
Yeah. So whenever you are interpreting a p-value, it is basically going to tell you the probability of observing this particular sample when the null hypothesis is assumed to be true. And when you are doing that, in this particular case, you are getting a probability of 63% almost. So which basically means, okay, this is said to be almost coming from the distribution. So you can accept the null. And a second way of looking at it is you give something called as the alpha value. And if the p-value is greater than the alpha, which is the significance level, then you can say, okay, the null hypothesis is acceptable. And the p-value, let's say I talk about the probability. I initially said the probability, right? So probability is a number. So you must compare that number, whether it is bigger or smaller, to something else. So that is the alpha value that you will compare it to. So for whatever alpha I take, whether it's 5% or 10% or 15%, this p-value is going to be greater than that. It's going to be greater than 0.05, 0.15, or let's say 0.10. So we will say that the null hypothesis is not rejected. You do not reject the null, and you will say this sample is coming from a Poisson.
There is another way to confirm this. So we did this using p-value. The other way is to look at the calculated chi-square value with respect to the tabulated chi-square value. So for that, I'm importing another library, I think, which we have already imported this. So let's run this. So scipy.stats.chi-square.ppf, it's going to give us the tabulated chi-square value for a confidence level of 95%. So therefore, I've used 1 minus 0.05. You can also give 0.95 directly. Here, the degrees of freedom is mentioned as 9. For chi-square, it's k minus p minus 1. So the parameter for chi-square is just the mean or lambda. So therefore, the p-value is 1 here. So we have 11 classes, that is k. So 11 minus 1 is 10, minus 1 is 9. So therefore, we have a degrees of freedom of 9. So Malo, you want to add something more to this?
Yeah. So in general, when you are doing a chi-square test, like Swami said, we are going to do k minus p minus 1, where k is the number of buckets that we have. So we have 11 buckets in this particular case. P is the number of parameters we estimate from the sample. Since we are only theorizing about the observation or about the distribution, our p value here is computed as the mean. So p is 1. Only the mean is being computed. Number 1. So k minus 1 minus 1, which is the formula, k minus p minus 1. So 11 minus 1 minus 1, which is 9 degrees of freedom. And as Swami rightly pointed out, he's putting it as 1 minus 0.05, where he's taking this alpha as 5%. So you can also directly give it as 95% or 0.95.
Yes.
And Yeah, and if this number that you're getting, for the interest of readers, should it be greater than, this is a question, should it be greater than the computed test statistic for you to accept the null hypothesis, or should it be lesser than the computed test statistic for you to accept the null hypothesis? So that is a question for you guys. Just pause, think about it. Then we will again show you what is the computed value. Over to you, Swami.
Yes, I hope you guys would have guessed it right. So now without any further delay, so let me run this and show you the, okay, I think I have to import this.
Yeah.
So we have a tabulated chi-square value of 16.91. So we can compare this with the calculated value, which is 7.9.
So the answer is actually, if our tabulated value is greater than our computed value, then do not reject the null hypothesis. So in this case, our tabulated value is greater than our computed value. So we do not reject the null hypothesis, and hence we can conclude that the Poisson distribution is the population from which our particular sample is coming from.
Exactly. So our guess was right. We guessed it as a Poisson, and it is a Poisson distribution. And Malo, so can you talk about some business cases for Poisson distribution?
Yeah. So let's go back to our data itself. Let's go back to our data.
Shall I open the Excel?
Yeah, you can open the Excel.
Let me clear the filter. Yes.
So this particular data set is just giving you numbers 5, 4, 4, 5. And the most common place where Poisson distributions usually occur are places where you have events happening. For example, let's say this was at a traffic signal in some Chennai location, where the number of times the signal was violated. So in a particular day. So in a particular day, let's say that was day 1, row number 2 is actually day 1, the signal was violated 5 times. In row number 3, the signal was violated 4 times on day number 2. So on each day, how many times anyone had violated that signal? So that is a count information. So this could be an example for such a scenario. You could also look at it from a different sense. Let's say you're manufacturing products. Every day you're manufacturing 1,000 products. Out of those 1,000 products, how many are defective? So 5 could be a defective on particular day's production. 4 could be a defect on the number of 4 units were of defect on another day of production, so on and so forth. So wherever you have count information, those places could be ideal for Poisson distributions to happen.
Great. So to put it in a nutshell, number of discrete events happening over a continuous space is Poisson distribution. The other examples could include customer arrivals and so on. So with this, we'll conclude the Poisson distribution.